Good morning, guys. I want to come to you real quick, talk to you about electron configuration, make sure that we all know what's going on with that. Three different types of electron configuration, or three different notations. You have the orbital notation, that's the one with the arrows, up arrows, down arrows. You have just regular electron configuration, and then we have what we call noble gas notation. Okay, each one of them is a little bit of an abbreviation of the one before, giving us a little bit less information, but taking less time to write, because as we move down the periodic table, it can become a lot of electrons there we're dealing with. So real quick, go over the three rules that govern electron configuration. Number one, we have Aufbau's principle that says it's going to go in the lowest energy level orbital that can receive it. So the 1s is going to completely fill up before the 2s, and then after that, then you're going to fill your 2p up. Now I know there's three 2p orbitals, and you're going to fill them up before you move on to the 3s. Okay, and then the 3Ps would completely fill up before you move on to the 4S. And then you would fill up the 3Ds completely before you move on to the 4Ps, and so on. Okay, lowest energy level first. Next one is Pauli's exclusion principle. Pauli's exclusion principle says that no two electrons can have the exact same set of quantum numbers, and that just simply means if we're talking about in orbital here, if we just talk about the 1s orbital, we take care of that in orbital notation by simply having one of them spinning up and one of them spinning down. So the arrows represent the electrons, right? So this one is spinning one direction, this one is spinning the other direction. That gives them a different set of quantum numbers. So even though they're in the same orbital, they don't have the same set of quantum numbers. So orbital notation, we take care of that with the arrows spinning in opposite direction if they're in the same orbital. Really, in noble gas notation, electron configuration, we just kind of assume that you understand and know that at that point. It's not, you don't actually see it in the notation anywhere. Okay? And then the last one is Hund's rule. Hund's rule says that everybody gets a room to themselves because it's less energy that way, right? So we'll each get each orbital. So if I say, for instance, the 3p orbital, so they come in a set of 3, p orbitals come in a set of 3, right? If you only have one electron, then the one electron just goes here. And even if you only have one electron in the 3p orbitals, I still have to have all 3p orbitals listed. So we can see, hey, they come in a set of 3, but we're only using one of them, right? So if we have a second electron, that second electron goes in its own orbital like this. It does not double up like this, okay? Why would it double up here and get closer to that electron than it has to be? Electrons have the same charge, they like to stay far apart, right? So it stays far apart by getting its own orbital, like so, okay? And both of these have to be spinning in the same direction. So we're going to go up, up. If you was to have a third electron in the p orbital, 3p orbitals, it would also be up. And then at that point, they all have one. So then if we had another electron, it would begin to double fill. Pauli's exclusion principle says it has to be spinning the opposite way. So then we would go down, and then down, and down. At this point, the 3p orbitals would be maxed out. So if I had another electron, then it would have to move on to the next energy level, which would be the 4s. Okay? So there's that. We're going to look at a couple problems real quick, showing you orbital notation, which we've done a little bit, but I just want to go ahead and put it on the video here, and then we'll do some electron configuration and some of the noble gas notation as well. Okay? So if we just take sodium, for example. Sodium Na, we can find it, if I come here, we can find it on the periodic table right here. It's, whoops, I touched. It's in the third period, so that means it's third energy level, right? And it's it's in group 1, so that means it has one electron in that s orbital, in the 3s orbital. Okay, remember s block, p block, d block. F block just simply tells me where its last electron is found. Sodium has 11 electrons, so I know that I'm going to have to represent 11 electrons here, right? So I've got the 1s, 2s, the 2p comes in a set of 3, and then I'm going to have 3s, right? So 11 electrons to work with, up, down, this energy level is filled, so we move on to the next one, up, down, that one's filled, so now we move on to the 2p's, right? And they fill up, 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 and then down, down, down. So that gives me 2, 4, 6, 8, 10 electrons. We needed 11, right? So we have one more here in the 3s. So there's sodium just like that, right? one more of those, I guess. Let's see. We'll do chromium. Okay? So chromium is here in the middle. If you look on your periodic table, you can see exactly where it is, but it's here in the middle of the 3D. Okay, so it lets me know I'm going to go all the way. I'm going to fill everything up all the way to the 3D, and then the 3D would partially fill since we're in the middle of this 3D. Okay, so it has its atomic number is 24, so it's got 24 electrons to work with because we're only dealing with neutral atoms here. We could deal with ions as well, but we're not. We're just dealing with neutral atoms. Okay, so we've got 1s, 2s, the 2 p's are all together here. If you want to kind of bracket it or something like that, or if you want to write 2p up under each one, it doesn't matter. 3s, 3p. I'm running out of room, so I'm going to come down here at the bottom to finish. 4s, and then your 3ds, there's 5 of them. Okay? So, like I said, 24 electrons. So start filling them up. 1, 2, 3, 4. I know these are going to completely fill, but I still fill them up, 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 and then come back down, 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 just to have the habit of using Hund's rule correctly. When I partially fill one, I don't accidentally fill it wrong. Okay? So that gets me to 10, 11, 12, 13, 14, 15, 16, 17, 18, right? 19, 20. So now I have 4 electrons left. So because we needed 24 for chromium, right now I have 20. So Hund's rule says I'm going to go up, 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 just like that, and that gets me to 24. So there's actually a 3D orbital here that's empty, that has nothing in it, but I still draw it so we can see that, hey, there's an orbital left that's not being used. And then of course the 3D would actually be able to hold, a second one in all of these after we filled this one up the first time as well. Okay? So there's that with orbital notation. Hopefully you kind of already have a hang of it just in case. And here's a couple extra problems. If not, you can get with me and ask me questions. Now let's look at the electron configuration. Electron configuration is an abbreviation of this, all right? So we get out of having to actually draw the lines and the arrows here, and we just simply say what orbitals and how many is in each of those orbitals, okay? Using this terminology here. 1s would be first energy level s orbital, right? 2s is second energy level s orbital. 2p, second energy level p orbital, right? So the electron configuration for sodium just looks like this, where we just simply say 1s, and then as a exponent or as a superscript, we say how many electrons are in that. So 2, okay? And then we have 2s, and there's 2 electrons in the 2s. And then we say 2p, and there is 6 electrons in the 2p. And then we have the 3s, and for sodium, remember 3s only has the 1, so we have 1 electron in the 3s. If I take and I add all of my superscripts, or I add all of my exponents up, 2, 4, 10, 11, I should get the number of electrons that sodium has. So sodium has 11 electrons, so boom, there's 11. That's it. It's easy peasy, okay? All you have to do is make sure that you put these in the right order, okay? You make sure that you put this in the right order. Make sure that you have the correct number. You don't overfill. You can't say that an s orbital has 3. You can't say that this s orbital has 1 and then go on and begin filling this, because that's breaking Aufbau's principle that you have to have this one filled before you move to that one. So you fill this up, fill this up, fill this up, fill this up, and keep on going. And in this case, this one was partially filled, so of course that's where we would stop. Okay? So obviously you can see this is a lot shorter than having to do it this way. All right? So if we let's look at another one of these. Let's go bromine. Okay? So bromine, we'll find it. It's in the P block. It's over here. It's group 17, right? So group 17, that automatically tells me that it's going to have 5 electrons in that P orbital that it's in. And bromine is in 2, 3, 4. It's in the 4P. So I automatically know, because it's located right here in the 4P, that it's going to end, this electrons configuration is going to end with 4p5 because it's the fifth one. It's in group 17, it's the fifth one in the 4p. Once again, when you look on your periodic table, you'll be able to see that, right? So that's how it's going to end. I just have to fill all the way up to that 4p5, all right? And of course, I can go back and I can count my electrons to make sure I have the right number. Bromine is 35, so I should have a total of 35 electrons, right? So 1s2, 2s2, 2p6, 3s2. And if you don't have the order memorized, remember it's just 1s, and then 2s, and then 2p's. Just follow along your periodic table. 3s, and then we're going to go to 3p. 3p holds 6. And then we're here 4s. It holds 2. 3d. It holds 10. And now we're into that 4p. So 4p, and it holds a total of 6, but we only need 5 more because we got 2, 4, 10, 12, 18, 20, 30, and we only need 5 more because bromine has 35 electrons when it's neutral, so 4p5. And once again, if you're looking on the periodic table, you will see that bromine is the 1, 2, 3, 4, 5th one over, with the noble gases being the 6th one with that completely filled outer valence shell. Okay? Easy enough? Yes? No? Let me know if you have any questions about this, but it's pretty cut and dry. The subscripts, the superscripts or the exponents just tell us how many electrons we have in each of those. Just make sure you're following Aufbau's principle and you have the orbitals in the correct order according to the way that they go in the periodic table. Okay, with the really the most confusing part being the d orbitals. Yes, the period kind of tells you the energy level in most cases, except for when it comes to the d's. Okay, so it's fourth period, so we're at 4s and 4p, but the 3d is actually coming after the 4s. So just because it's in the fourth period, right, doesn't mean that's a 4d. And an easy thing to remember there is just, okay, where does the d orbital start? If we know this is the d block, the top row would have to be the first set of d orbitals, right? So we know from what we've learned in the past with the orbitals, right, that the first energy level just has s, the second energy level has s and p, this the third energy level that has the d. So the first set of d's would have to be the 3 d's, right? And as a rule of thumb, of course, we're just taking whatever period we're in and subtracting 1 to find whichever d orbital is. If you just remember, hey, it starts with 3d, then it just follows 3, 4, 5, 6, that kind of thing, okay? The 4f, it starts with 4f. Fourth energy level is the first one that has an f block, right? So the top f would have to be 4f. And remember, it comes in right, it comes in right here between the 6s and the 5d. Now, there are some exceptions to these electron configurations, and there's some exceptions to the order that it fills. Sometimes electrons do funny stuff because it's trying to get the lowest energy level possible. So it sometimes don't follow the trend. We're not doing any exceptions. So if you look up any of these and you get a different answer, you look at the back of the textbook and it has the electron configuration or the noble gas notation, and you see this is a different answer, especially in here or in here. It never really breaks the rule or the trend with the S or the P's, but sometimes with the D's and the F it does funny stuff. Don't worry about that. You just do what you would think it would do based on the number that it has, okay? So occasionally there's something funny going on, but don't worry about that. I'm not testing you. I'm not expecting you to understand exceptions to the rule. I'm expecting you to just simply understand the rule, okay? There's that. All right. And let's do noble gas notation. Can I see you in just a second? Okay. Let's do noble gas notation real quick. And let's work with, let's do chlorine, okay? We'll work with chlorine. First, I'll go ahead, how about this? I'll go ahead and do all three of them with chlorine. So chlorine is in our 3P. It's once again group 17, so it's going to be a 3P5. So we're going to fill all the way up to there. So if I do orbital notation, you've got 1s, 2s, 2p, 3s, and then I'll squeeze 3p in there, right? So chlorine 17 electrons, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, right? So orbital notation, that's what it looks like. If we're doing electron configuration, then we're simply just basically getting rid of the arrows and replacing it with just the exponents just telling us how many electrons are there. So 1s, there's 2, 2s, there's 2, 2p, there's 6, 3s, there's 2, and 3p, there's 5. Done deal, right? If we're doing noble gas notation is an abbreviation that allows us to basically go off what the previous noble gas was, okay? So if we look at what the previous noble gas was, if you're looking at chlorine, chlorine's here, right? So its previous noble gas, all right? So, yeah, that'll work. So chlorine's right here, right? Its previous noble gas, I don't know if you can read that, is neon right here, okay? So rather than writing this whole, probably making it harder and harder to read, okay? Rather than writing the whole electron configuration for chlorine, what we do is we use a noble gas that is before that. So whatever row we're on, if we'll go up the row and go to the end of that, then we have the noble gas that's right before it, okay? So whatever period we're on, right? The noble gas before that. So go up, and obviously noble gases are all the way at the end, and you will find the noble gas before it, all right? So we abbreviate it by just putting that in brackets here, okay? Putting that symbol in brackets. So neon would be the noble gas that comes right before chlorine, okay? If you go back, the first one you get to is neon. So we'd say neon core, right? And what we're saying is, all of the inner shell electrons of chlorine have the same electron configuration as neon. Okay, so it's a neon core, and then we're just going to list the electrons that's in that outer shell, just on that valence shell. So just the electrons that's in the row that chlorine's in. Okay, so we've already taken care of the first 10 electrons. All right, and then after that, after neon, we're to the 3s. So then we'd have to say 3s. And there's 2 there, and then 3p, and chlorine's the 5th one, so it's 3p5. All right? So what we did is we replaced writing all of this, because that is the inner shell electrons. That's on those lower energy levels, right? That's on the higher periods. We replaced all of this. This would be neon's electron configuration. So we just simply said, hey, neon core, and then we had to write this part down, just the 3s2, 3p5, okay? So here, it saves us a little bit, but as you go further down, then it gets longer and longer, and it's going to save you more and more time and effort being able to do this, okay? And once again, it's called noble gas configuration, okay? Noble gas notation. So we're only using noble gases. We can't just pick any element we want, and we're using the noble gases because the noble gases is where an energy level gets completely filled, right? So we're saying, okay, the first 2 energy levels are completely filled with neon core, and then chlorine's outer shell, that outer ring, if you're thinking about it as far as the Bohr model goes, has 7 more electrons in it, right? So these are the outer shell or valence electrons, and then here's the core electrons or inner shell for chlorine, all right? So let's look at one more of those, and then maybe you'll be good, all right? I won't do the orbital notation for this one, but I will do the electron configuration first. So let's move on down a little bit. Yeah. Let's go with 10. This one's gonna be pretty big when we write our there we go. 10 is found in the, this real quick. 10 is found in the 5p, okay? It's found right here. It's the second one in the 5p, Okay, so if we're doing electron configuration, then we have to say all of these electrons all the way up here to this 10. Yeah, the symbol is SN. Okay, but then when we do the noble gas notation, we will come back up here and we would just look at whatever this noble gas is right above it. The row above, obviously noble gases are all the way at the end, and just making sure, yeah. So this would be Kr krypton. All right. So first, I will do the electron configuration. So 1s, 2, 2s, 2p6. Once again, Aufbau's principle tells me the order. I can just see the order on here. 3s2, 3p6, 4s2, 3d10. Right? The orbitals hold 10. 4p6. We have 5s2. I don't want to get behind the TV so you can't see, so I'm going to bring this down here. 5s2, and then after that we have 4d10, right? 5s and then 4d, and then we get into the 5p. So we're at 5p, and it's the second one where it's in group 14. All right, so group 13 is the first, group 14 will be the second of the p's. So 5p2, and we can imagine what that would look like as far as orbital notation, right? 5p's. We would have one electron and then another electron, right? So if we need a visual of that, orbital notation gives us that. There's two of them, boom, boom. But we don't have to write all of that other stuff because that would take a while, right? So electron configuration there for 10. If we're doing the noble gas notation for 10, then we get to say, okay, all of the first, 36 electrons are taken care of by just saying krypton core. Okay, put krypton in brackets, krypton core, and then we just have to list the electrons that's on this fifth period. Okay, so that's starting with 5s2, 4d10, and then 5p2. So once again, all of these guys, all the way up here to this 4p6, and a full p shell is always going to be the end of a energy level, right? So, well, technically here, this is the end of the first energy level, then right here, 2p6, end of the second energy level, 3p6, end of the third energy level, and then 4p6, end of the fourth energy level, right? So the first four energy levels are all taken care of right here with krypton core. That's the inner shell electrons, and then the electrons that's on that outer shell would be these guys, okay? Now, don't get confused. It's just the s and p orbitals that play a part as far as the valence electrons go. So yeah, these 10 electrons that's in this 4d orbital is in this row, so to speak, but it's not counted as a valence electron because technically it's the fourth energy level. Okay, but yeah, we do have to list them because they're not listed before that. All right, so 10. Krypton core, 5s2, 4d10, 5p2. Okay, I think that's pretty easy. If you have any questions, let me know. Got a few worksheets we're going to do today over practicing this stuff. Some of them are just doing electron configuration. Some of them, some of the worksheets is a mix of all of it. So you do some of each of them, like I did with chlorine, where I did all three of them. So there's a little bit of that as well. All right. Excellent.